Thank you so much for the introduction, and thank you to everyone for coming to my talk. As said, I'm Juliette Bruce, and I'm a new postdoc at the University of California, Berkeley. And for the year, I am also in residence at MSRI, which is why I'm in this lovely office all to myself. And today I'm going to talk about the top-weight cohomology of the moduli space of principally polarized abelian varieties of dimension G, also known as AG. And I will say at the beginning that this is all joint work with a long list of authors, namely Madeline Brandt, Melody Chan, both of whom were at Brown, Margarida Melo, who is at Roma, Gwyneth Moreland at Harvard, and Corey Wolfe at Tulane. And so the central player throughout this talk is going to be AG, which is the moduli space of principally polarized abelian varieties of dimension G. So an abelian variety is just a projective variety that has a group structure where the group operations are regular maps. So they're given by polynomials. So a quintessential example you might want to think of is an elliptic curve. So an elliptic curve is a projective variety, and it has a group structure on it. And so that is a example of an abelian variety of dimension 1, and we have higher dimensional analogs of these. And a principal polarization is a type of kind of extra gadget, extra structure we need to specify in order to form a nice moduli space. And you can think about it as essentially being an embedding if you would like. And AG is just some space whose points parameterize these abelian varieties together with this extra structure. And the important thing I want to note, because it will come up throughout various points of the talk, is that the dimension of this space, so the dimension of AG is G plus 1 choose 2, and throughout my talk that will often be referred to as D. So if you see the letter D anywhere, that's just the dimension of AG. And the question that this work all began with, I think in some ways, is a question of Grishevsky. From 2009, which asks, does AG have odd cohomology for some G, right? Put differently, for some G, is there a non-trivial odd cohomology group of the moduli space of principally polarized abelian varieties of dimension G? I should say throughout this entire talk, unless I say otherwise, all the cohomology I'm talking about is just going to be rational cohomology. So really, I'm just asking whether this vector space is non-zero or not in odd degree. And as far as I know, this question is still open until what I'm about to tell you, maybe in about 10 minutes. But why, I think before I get there, I want to kind of review some previous work in this vein and ask kind of why would we ask this question? So what's the motivation for this question? Because it's a bit of an odd one if you've never thought about these things. So what was previously known in this vein? So in 1962, Agusa computed the cohomology ring of A2. So he was able to show that the cohomology of A2 with rational coefficients was either Q if K was 0 or 2 and 0 otherwise. Okay. In 40 years later, in 2002, Hain did the next case, namely computing the cohomology ring of A3, and he showed that there were 3 cases to consider, namely if K was 0, 2, or 4, the cohomology was isomorphic to Q. It was two-dimensional if K was equal to 6, and it was zero-dimensional otherwise. Okay? And really, this is all that was known about the cohomology of AG in the direction of Grzyszewski's question. Certainly other things were known. For example, the stable cohomology or the orbifold Euler characteristic are things that were known classically. But if we actually wanted to talk about, can we really understand the rational cohomology explicitly, really the result of Agusa for A2 and the work of Hayne for A3 is all that was known in the direction of this question. And looking at these two examples, we might wonder, why is it a question of does it exist? And well, and not a conjecture that it doesn't, because certainly in these two examples, there is no odd cohomology. So we might guess from the examples that it just doesn't happen. But I think the reason for that it's a question of does it exist is around the time Grzyszewski was asking this in 2005 or 2007, Tomasi showed the following. That H5 of M4 with rational coefficients is in fact non-zero and isomorphic to Q. So not the moduli space of abelian varieties, but instead looking at the moduli space of genus 4 curves, Tomasi was able to show that there is a non-trivial odd cohomology class for M4. And in fact, this was the first known odd cohomology class for MG or AG. And given the close connection between these two moduli spaces, given by the Trelli map and other ways, we might speculate kind of that if MG has odd cohomology, then AG is also likely to have odd cohomology. So I think Grzyszewski's question is very much in the vein of, okay, it happens for M4, can it happen for A4 or other kind of G? But I think in a bigger picture, what really is going on here is that it turns out getting at odd cohomology groups is quite difficult. So as algebraic geometers, often our standard techniques produce things that are varieties over the complex numbers, which then naturally live in even degree cohomology since everything is going to have real dimension 2k. So finding non-trivial odd cohomology turns out to be quite difficult. As I just said, until very, very recently, the only odd cohomology class known for either MG or AG was this single example in genus 4. And so that gets me to kind of one of the two main theorems I want to say today. And so this theorem is again due to myself, Madeline Brandt, Melody Chan, Margarida Melo, Gwyneth Moreland, and Corey Wolfe. And it says, for G between 2 and 7, the top weight cohomology of AG is 0, except in the following cases. So I have a nice big long list of cases. So when for A3, the top weight cohomology is non-trivial. When K is 6, when G is 5, the top weight cohomology of A5 is non-trivial when K is 15 or 20. Let's see, for A6, it's non-trivial when K is 30. I should say GRW, put a dot there. And finally, for A7, the top weight cohomology is non-trivial when K is either 28, 33, 37, or 42. Okay, and again, GRW dot. Okay, and so let me unpack this. So I'm saying all the moduli space of principally polarized abelian varieties for G between 2 and 7, we're able to fully compute the top weight cohomology. And what is that? So by Deling's theory of Hodge structures, the weight filtration of AG is supported in degrees 2 from 0 up to twice the dimension. And kind of the top weight cohomology piece is the one in top weight, so the piece in degree 2 times the dimension, so in degree 2D. Alternatively, if you prefer not to think about Hodge theory very much, what we can just think about is that the top weight cohomology of AG is a canonical quotient of the cohomology. So what we have is that if we look at the cohomology of AG in degree K, the top weight cohomology, which I denote GR, W, and either dot, or if I'm being careful, 2D to signify its weight of HK of AG is a canonical quotient of AG. So in particular,
excuse me, sorry to interrupt.
No, you're good.
That quotient is the quotient by the image of the compactification, smooth compactification of AG, or weight.
Not quite. So this quotient is essentially, so the weight filtration gives you a filtration, and you take the associated graded according to that filtration coming from Hodge-Dilling's theory of weights, and the top graded piece is this top associated graded thing.
Yeah, but I was right. So I guess I was trying to remember that I thought there was a theorem that when you have a smooth compactification, the graded piece of the top weight is the, well, wait, what am I trying to say?
So you're thinking
smooth
that if you have
compactification, if you take, of course, AG has a smooth compactification, the whatever you call it. I mean, there are various ones. I mean, you could take the Mumford compactification, the toroidal compactification, and of course you have a map. So AG embeds into AG bar, and so there's a map from AG bar, and the image of that, I thought, now maybe I'm forgetting my Hodge theory, is giving you the top weighted piece.
Yes.
Am I forgetting something?
So you're right on track for the most part. So if you have a nice space and you take a compactification that is smooth, such that the divisor has strictly normal crossings, then there's a spectral sequence argument that will say that the top weight cohomology can be computed by the boundary complex of this compactification. And that's almost the idea here, but I'll point out that in fact, Mumford's compactification of AG is not smooth. So it has singularities.
Well, it has internal singularities that come from, well, what you might call the finite quotient singularities.
Mm-hmm.
But you're taking rational cohomology, so I don't know if that's so much of a problem, the compactifications inside.
Sorry, Phil, can I just say something?
Yeah.
I think you're getting confused because I think the theorem you're thinking tells you the bottom weight. And your maps are going the opposite way.
Oh, so this is the part of lowest weight. Okay, so maybe I'm upside down here.
Mm-hmm. So so at some point I'll get to how we actually prove this, and that might help clarify this question.
Okay.
But the important point is that, right, this is a canonical quotient. So in particular, if the top weight cohomology is non-trivial, then that corresponding cohomology group is also non-trivial. So in particular, looking through the list, right, k equals 15 for A5, and k equals 33 and 37 for A7 all produce non-trivial odd cohomology classes of AG, answering Grishevsky's question affirmatively, right? So I will also say this almost doubles the total number of non-trivial odd cohomology classes we knew for either AG and MG. before this work, there were, I think, 3 or 4 classes known for MG, and now there are 3 classes known for AG. So this kind of tells us a lot more about this in this vein of this question. But really what I want to talk about is kind of getting at the questions that have been asked, which is, where is this coming from? And so what's going into this theorem? And so with that in mind, what we're actually able to show, and I'm going to state this theorem somewhat vaguely, and again, it's all with the same set of co-authors, is that there's a chain complex, and I'm going to call it some combinatorial chain complex, P upper G dot, which we call the perfect complex, such that there's a canonical isomorphism between the homology of this chain complex and the top graded piece of the top weight cohomology of AG with an appropriate shift of degrees. So how do we prove the first theorem from the second? Well, we're able to explicitly write down this chain complex for G up to 7 and compute all of the homology in sight, thus computing all the top weight cohomology of AG. And what I really want to kind of talk about for the rest of the talk is, what exactly is this complex, PG, and where does this isomorphism come from? Because I think really the interesting aspect of what we're doing here, well, it's nice to get results, but also is kind of to build a new theory to allow us to start to understand the cohomology of AG in a new perspective, right? I think Grishevsky's question was really asking for a new approach to finding cohomology classes, and I think this is one of them that certainly builds on a current kind of thread throughout this, in this vein. And so I said this complex is combinatorial in nature, so it's going to take me a little while to set everything up. And if you're an expert on AG, you might expect where this is going pretty quickly, but if you haven't seen this before, stick with me. So going from now on, omega lower G is going to be the set of positive definite G by G quadratic forms over the real numbers. So I'm going to think about these as being G by G symmetric matrices that are also positive definite. So it lives in some big vector space R to the G plus 1 choose 2. Okay, and so it turns out that this forms some sort of cone. So it's a non-polyhedral cone, but it is convex and it's not closed. It's very much open. So I have the picture is I have some cone consisting of all the positive definite matrices. I'll note that even the cone point isn't in this cone, so it's a little bit of a strange cone to consider. And then I'm going to let omega G upper RT be a slight closure of this set. So what do I mean? I mean, it's going to be the set of positive semi-definite G by G quadratic forms but I'm only going to take those positive semi-definite quadratic forms that have rational kernel. So what I mean is I take my quadratic form, I look at the kernel, and I ask whether or not I can have a basis for that consisting of just vectors with rational coefficients. Okay, and so this again forms some cone, and I want to think about it as being essentially kind of as throwing in a lot of points along the boundary. So it isn't itself closed because the closure of this cone would be the set of all positive semi-definite matrices. But for example, it throws in like things like the cone point. So the cone point would correspond to the matrix of all zeros, and that matrix is positive semi-definite, and it has rational kernel. And so that matrix is in there. And this is maybe a strange thing to do because I'm not fully closing up my cone, but the kind of analog I want to think about is that if you've seen the construction of M11 bar, when you want to take the compactification, you have to take the upper half plane, and then you have to throw in all the points along the boundary of the upper half plane who have rational coordinates. And so this is somehow kind of an analog of it. It turns out throwing in the entire, all positive semi-definite matrices would be too much. And then an important thing that I want to notice here is that there's a natural action of GLGZ on this cone. So on this cone, we have an action of GLGZ given by taking a matrix X and sending it to A, X, A transpose, right? So kind of conjugating the cone by GLGZ. And I will just say briefly, if I say it earlier, this is often known as the rational closure. Of omega G. So we're getting closer to combinatorics. I now have a cone, and that's pretty combinatorial, but it's not polyhedral, and it's not a rational cone. And so what I need is I need to find a way to approximate it by well-behaved rational cones. And so this leads to a slightly technical definition, but one of an immiscible decomposition. So an admissible decomposition omega GRT is a set capital sigma consisting of little sigmas of rational polyhedral cones so my cones are always going to be little sigmas satisfying some conditions, and those conditions are, well, first, sigma has to cover omega GRT. So if I take the union of all the cones in this collection, I get omega GRT. Secondly, sigma has to behave well with respect to cone operation, so is closed under intersections and faces. So if I take a face of a cone in sigma, it's also in sigma, and if I take the intersection of two cones, they meet in a face, and that face is also in sigma. And a priori, since omega GRT is not a polyhedral cone, there are going to be infinitely many things in capital sigma. But up to the action, we're going to see that the next two conditions require that these cones behave well with respect to the action of GLGZ, and then also there are really only finitely many of them in that sense. So the next condition is that given an element of GLGZ and a cone, sigma in my set, A sigma A transpose is also in sigma. So GLGZ doesn't have to fix each individual cone as a set, but as a collection, it has to fix my collection. And finally, I have to have a finite number of GLGZ orbits. So again, sigma is going to be infinite, but up to the action of GLGZ, there are only finitely many cones. So how do I want to picture this thing? So I'm specifying some number, like a finite collection of rational polyhedral cones. So maybe this set of cones I've drawn here, and then I start letting GLGZ act. And as I do that, GLGZ is going to start moving these cones around in interesting ways, and they're going to start to spread out and fill up the space, and slowly tessellate all of this cone in a very fractal-like pattern. We'll see kind of a better picture of this in a second. But this is the idea of a immiscible decomposition. And just to make sure we're on the same page, let me give you an example of one of these. So the example I want to consider is the so-called perfect cone immiscible decomposition. And so the recipe for this is that you give me a positive definite quadratic form Q, so something in omega G, and then we first construct the set M of Q, which is going to be the set of non-zero lattice vectors in C to the G that minimize my quadratic form Q when I restrict it to the lattice. So what do I mean? I mean, if I think about Q and as a function just on the lattice without 0, X has to be a vector that minimizes that function. It might not minimize it globally, but on this lattice it does. So essentially, I'm looking at the vectors of shortest length with respect to the this quadratic form Q. I then need to make a cone. So what do? I let sigma of Q be the cone whose rays are all of the form x transpose, where x is is in the set M of Q. So I found the integer vectors of shortest length, and now I'm creating rank 1 matrices out of those vectors by doing x transpose. So, right, this is going to be a rank 1 quadratic form. Okay, and finally, the actual decomposition, the set of all such cones, is going to be my admissible decomposition. So sigma p lower g, which is going to be the set of omega q, or sorry, sigma q as we run over all positive definite quadratic forms. So this is an infinite collection of cones, but I claim that up to the action of GLGZ, it's finite, and it also satisfies all these other nice properties. And this turns out to be something that's quite classical. It's the result of Voronoi from 1908 that sigma upper p lower g is in fact an admissible decomposition. Okay, so in practice, what does this look like? So in practice, I have to give you a quadratic form, right? So let's write down a quadratic form. I'm going to do the example when G equals 2. So I'm looking at 2 by 2 symmetric matrices. So what quadratic form? Let's pick at least my favorite one, which is 1's on the diagonal and 1/2's on the off diagonal, which gives you the quadratic form x squared plus xy plus y squared. And so now I have to find the integer vectors that have minimized this function. Can anyone give me any of them? I'll give you a hint. The minimum value is 1. And so, for example, plus or minus 1, 0 is a shortest vector. We also get plus or minus 0, 1, and then plus or minus 1, comma, minus 1, right? So if you evaluate this quadratic form at any of these vectors, you get 1, and that's the smallest value this function can take on the integers. Okay, so that's my set of minimizing vectors, and then I have to form a cone. And so sigma of q is going to be the cone whose rays, well, I have to take each of these vectors and do vector transpose to make a rank 1 matrix. And when I do that, I'm going to get 3 matrices, 1, 0, 0, 0, 0, 0, 0, 1, and 1, -1, -1, 1. So these are the 3 rays of this cone. So this is a 3-dimensional cone in R3. And why is it in R3? Because I'm looking at 2 by 2 symmetric matrices, so that lives in, that's in R3. So pictorially, let me show you what this looks like. So let me quickly grab my picture and scroll back up. So I said we're looking at a cone in R3, so omega 2 RT lives in R3, and so to draw the cone, I'm going to take a hyperplane section of this cone and just look at the picture kind of the hyperplane section, and so that's what I'm looking at here. And then I said I had 3 rays, namely 1, 0, 0, 0, 0, 0, 0, 1, 1, -1, -1, 1. So these are the 3 rays. Let's not erase my picture. And so this cone here that I'm kind of colored in gray and now coloring in red is omega of this quadratic form Q. And it turns out if you start letting GL2Z act on this cone, you'll see that this quadratic form will flip over here, and then it will flip over here, and then it will flip over here, and it will slowly tessellate all of this cone. So in fact, up to the action of GL2Z, there's only one quadratic form of top dimension, namely this cone here. So all the cones in the perfect cone decomposition of omega 2 RT is given by taking this single cone here, known as the principal cone, and then all the faces and rays thereof. So I have this kind of face here as a cone, the ray is also a cone, and these are all of the cones in my admissible decomposition. Okay, and so I'm almost at the point where I can tell you what this chain complex is. So how do we actually construct the chain complex? But I need one more definition. And that definition is that we say a cone, sigma, is alternating if and only if given an element of A in GLGZ, let's see, such that A sigma A transpose is equals sigma, then A is orientation preserving on sigma. So what do I mean? So I mean, I have an element of GLGZ acting, and I assume that it's taking sigma to sigma, which means if I restrict to sigma, I get a map of manifolds with boundaries or manifolds with corners from sigma to sigma. And as a map of manifolds with boundary, that map induced by the matrix A has to be orientation preserving on sigma. And we call such cones alternating. So as an example, I claim, and I'll let you think about it for a second before I spoil the answer, that the cone that we just created, the principal cone that I'm coloring in red, is not alternating. Namely, you can find an element of GL2Z that's going to induce an orientation reversing automorphism of this cone. So I'll leave you to think about that for a minute while I introduce the definition. So I can now finally define the chain complex. So we define the chain complex P upper G lower dot to be, well, as a vector space in dimension K, it's the Q vector space spanned by the GLGZ orbits of alternating cones sigma in this admissible decomposition, in the perfect cone decomposition, with the dimension of sigma equaling k plus 1. So I look at all in degree k, this chain complex is generated by the orbits of cones of dimension k plus 1 that don't have orientation reversing stabilizers. Note that by the definition of an immiscible decomposition, there's necessarily a finite number of these things. So this is a nice finite vector space. And now I have to define for you the differential. And so the differential omega k, or sorry, the differential takes in a cone sigma, and it's going to spit out a sum over all the codimension 1 faces of sigma. So tau is a codimension 1 face, a facet of my cone. And then it's going to be minus 1 to something, and I'll say something about that in a second, times the class of that facet. Okay. And so you gave me a cone, and I take the sum over all the codimension 1 faces, and I put some signs in there. And what signs do I put in here? So what is this minus 1 to the something? I haven't told you. Well, one answer is, I'll give 3 answers, I guess, in increasing order of correctness. The first answer is that it's whatever sign you need to make it a chain complex. The second answer, which is slightly better, is that it's the sign convention that you always use when you're writing down a cellular chain complex. And the third one in the most correct version is that you fix a reference orientation on all of your cones, and then you say that tau gets plus 1 if the orientation induced from sigma agrees with the reference orientation you picked for tau, and if the induced orientation and the reference orientation disagree, you give it a minus sign. So it's a proposition in our paper that you can show that this is in fact a chain complex. And so let's look at this in a really specific example. So continuing the running example, where G equals 3, or sorry, G equals 2. So this is going to be a chain complex, and it.
Ask a question.
Yeah.
So, what if tau is not alternating? Do you ignore it, or does that not happen?
So in that case, we just kind of say the class of tau is 0, right? And it doesn't. We don't have to worry about that. But that's a good question. So when G equals 2, I have cone. We already saw that the maximal dimension cone is 3. So my chain complex is supported in degrees 2 down to degrees minus 1, because we have this weird shift where we're putting dimension k plus 1 cones in degree k. And so now I need to grab my next picture. Okay, so we already said that in top dimension, there's at most 1 cone up to the action of GLGZ, namely sigma of 2 here that I've colored in gray is the only cone. And I've also already told you or claimed that its orientation is not alternating. And the reason it's not alternating is because there's an element of GL2Z that's going to reflect sigma 2 across the red line. So it's going to kind of mirror it over itself, and this mirroring action is definitely not orientation preserving. So this 1 cone, which is the only cone up to GL2Z, is not alternating. So in degree 2, my chain complex is 0. Okay. It turns out that GL2Z acts transitively on all cones in this space and this decomposition. So in particular, there's at most 1 cone in each dimension. So for example, in dimension 2, the only cone to consider is the one I've just shaded in red, which I've labeled sigma 1 and colored in purple in my diagram. And again, we have to now decide if that's alternating. And for the same reason as sigma 2, it's not alternating, because the same element that flipped my big cone over this line will reflect sigma, the purple cone also over the line. So in degree 1, this chain complex is also 0. And then finally, we have to look at the last two cones, namely array and the cone point, which lives in degree 0 and degree 0 and 1 respectively, and decide if they're alternating. Well, since the cone point is always fixed, array is always going to be alternating because you can't move that cone point around. So it turns out that this chain complex is going to be zeros, and then here I have a Q, and here I have a Q, and here I have a 0, and this map is going to be either 1 or -1, depending on what reference orientation we picked, but either way, it's going to be an isomorphism. So what we just saw is that we've constructed this chain complex, and we see that the homology of P2 is trivial for all k. And by that theorem, by our second theorem, what this actually tells us is that the top weight cohomology of A2 is also trivial for all k. So altogether now, we've just managed to compute the top weight cohomology of A2 and recover what's essentially implicit in Agusa's work from 1962, namely that there is no top weight cohomology of A2. And now the name of the game is, to prove the first theorem, is just to kind of continue this thing. Write down the perfect cone decomposition for A3 and A4 and A5 and A6 and A7. Find out which cones are alternating, figure out what the differentials are, compute the homology, and there you go, we have the top weight cohomology. But with the last few minutes I have left, I want to briefly talk about where this isomorphism is coming from. So why is the homology of this chain complex isomorphic to the top weight cohomology of AG? And this will kind of hint at a question I think was earlier. And so I need two facts. Put this here. So I need two facts. And the facts are that the data of an admissible decomposition sigma specifies two things. So first, as was kind of already hinted, it specifies a toroidal compactification of AG inside, which I'm going to denote AG bar upper sigma. And this is originally work of Ash, Mumford, Rappaport, and Tai, and then later Faltings and Chai, kind of in a more general setting of stacks. And the second thing is that this data of an admissible decomposition specifies the moduli space of tropical abelian varieties. And I haven't said what these are, and I'm not going to, since I'm almost out of time, but there is a notion of a tropical moduli space of abelian varieties that was due to Bernetti, Melo, and Viviani, and Chan, Melo, and Viviani. And somehow the data you need to construct this is exactly the data of an admissible decomposition of omega GRT. And so now I can kind of quickly sketch what's going on in the proof of this theorem. And so on one side, I said we had the homology of this chain complex, PG. And on the other side, I said we had the top weight cohomology, I guess, sorry, with some shift in degrees of AG. Okay. And I need to build an isomorphism between these two things. And so where is this isomorphism coming from? Well, the first thing to note is that this chain complex, what it's actually computing is the reduced homology of the tropical moduli space. So there's an isomorphism between this chain complex and the reduced homology of AG trop sigma. So whatever the moduli space of tropical abelian varieties is, it's some topological space whose reduced homology I can take, and this chain complex is exactly computing that homology. And on the other side, as was already hinted, what is going on here, in fact, is that the top weight cohomology is the reduced homology of the boundary complex of AG in AG bar, where AG bar is coming from this toroidal compactification. This is not, you can kind of define this boundary complex in general, but it's not obvious, I think, at least from the existing literature necessarily, exactly what's going on in the situation we care about, because things are singular. And so we can have singularities, and that can cause some issues. It turns out it doesn't. And the easiest way to see that is that these two spaces down here, the boundary complex and the homology of the boundary complex and the homology of the moduli space of tropical abelian varieties is in fact isomorphic. And this homology here is independent of the choice of admissible decomposition. So it turns out the homeomorphism type of the moduli space of tropical abelian varieties does not depend on the admissible decomposition you pick. And what this means is, if you have a singular compactification, take a barycentric subdivision until eventually everything is smooth. On the toric side, it's clear that the homology of those things are going to be the same because the homeomorphism type is the same. And so this isomorphism kind of lets you circumvent the issues with smoothness that are at least implicit in what we know of is the existing literature. And so this isomorphism here is really going from this complex to tropical geometry to the boundary complex and back up. Okay, and finally, with the last minute, why did we stop at 7? And there's two answers to that question. One, a lot has already been, as I hinted, the perfect cone decomposition is something very classical. It dates back to Voronoi, and a lot has been computed about it already. So when I said we computed all the cones that were alternating, that was a slight lie. I'm saying it exists in the literature to find, and the literature kind of starts to peter out around g = 7. And the reason for that is, well, here is a table of g, and then the number of cones only in top dimension. So it starts off pretty innocently. There's one cone, and then one cone, and one cone, and I think these first 3 cases were all things Voronoi computed in 1908. Then you get 2 and 3 and 7, and by the time you're at g = 7, there's 33 top dimensional cones, let alone taking all of the possible faces. At 8, there's over 10,000, and at 9, we don't know how many there are. And there are very fast algorithms to compute these sorts of things, but we have yet to fully compute them all. But we know there's at least 500,000 such cones. And so the kind of naive approach of actually writing down this complex in full and computing all of its homology is probably going to run out right around where we stopped. You might get a little bit further if you're clever and very good at programming, but really, I think the next step is to kind of recognize, is to use this machinery that we've kind of built with this chain complex and these isomorphisms to construct non-trivial cohomology classes, kind of using combinatorics and other things. And this is kind of very much in the spirit of what Sam Payne, Melody Chan, and Soren Galetas did for the moduli space of curves. So I think that's kind of the next question, is how can we construct classes combinatorially via this chain complex? And I'll stop here and thank you all for listening.
Well, who's in charge here? Does anybody have any questions for our speaker? Well, I just have one or two. I mean, what I understand about compactifications really comes from the toroidal side, where you're looking at an algebro-geometric compactification. And as Moses pointed out, I had the whole picture upside down. I was looking at the lowest weight, not the highest weight. Let me understand what you're doing. You're only looking at the top weight, So from the compactification point of view, if you think of the Satake compactification, you have a stratification according to codimension. It seems as if you're going to the deepest part. In other words, you're only looking at the boundary component of, in this sense, of deepest deepest codimension in terms of the Satake compactification. In other words, when you do a toroidal compactification, you have cones of all kinds of dimensions depending on where you are. So you have codimension 1, codimension 2, codimension 3, and so on. And you went all the way up to the top depth, namely G. Right. So couldn't you go to some other depth? I mean, instead of doing top weight, why not do next to top weight? I mean, there should be a complex there too.
I think that's a great question. And I think you might be able to get something that works there. I would be a little bit concerned about whether, let me think for 1 second. So I think that's a great question. And I think whether or not you can get a complex that nicely computes kind of the top weight -1 cohomology or something like this, or the top weight -2 or 3, whatever, really comes down to whether you could understand there's two questions: whether you could understand what's going on the combinatorial side, and B, whether or not you can understand what the homology of this boundary divisor is going to converge to. So, right, really, I think, right, why are we getting this isomorphism? It's coming from a kind of the Mayer-Vittori spectral sequence, which is, since we're in top weight, all the maps are going to have to quickly become 0. So it kind of degenerates very quickly. And I think if you're looking at non-top weight cohomology, so top weight -1, you might have non-trivial maps that make things more difficult to analyze. But it's a great question. I think it's not something I've thought much about. So those are kind of my initial reactions, but I think it would be a very interesting thing to consider.
See, the way I think about it, I think about these boundary components as algebraic geometry things. So you have as you say, a divisor with normal crossings. And then you're looking at, in Deline's complex, you're looking at the intersections in there. So I would wonder about the relationship between your picture and that picture. So you're getting these boundary component. There's another way to try and compute this, would be to use that complex. And of course, it's not obvious at all how your complex, at least not in my mind, how your complex would relate to Deline's complex. I mean, there is one. When you have a smooth compactification, you have these divisors with normal crossings. There's a natural spectral sequence which relates to the intersection K by K of those divisors. So what you end up with is you look at the K by K intersections of these divisors, and they form a big complex.
Yes.
And so you're going in some sense, the top, the top weight, or the top boundary, or the deepest boundary component where all the components come together. And so I would wonder if you could, I don't know if it's worth it, but I wonder how it would relate to that picture. Your picture relates to Deline's picture of these boundary components.
I mean, I think secretly that really this complex, I think secretly it's really all of the same thing for top weight cohomology, right? So, I mean, they're isomorphic, as I've said, but at least in my head, they're all kind of seeing the same thing. So for example, if you knew how to construct this chain complex PG and you didn't like tropical geometry, you could probably cut out this lower thing and just phrase it as an explicit isomorphism of chain complexes with the Ling's complex or something like this.
Yeah, I think the problem though is that it's exactly computing the differentials.
Yeah.
You see, your complex has the advantage of concreteness in terms of boundary maps. And I'm not sure how explicit one could make those differentials in Deline's complex.
Yeah, I think that would be another thing that would have to be, one would have to think carefully about and might run into trouble there.
Well, does anybody else have any other questions? I mean, does anybody else want to ask a question?
I'm just trying to follow your conversation here. So the weights, the higher weights are supposed to come from something to do with what you're adding to a compactification. I guess my first question is, AG is a smooth variety?
So AG is a smooth but not proper variety.
Okay.
I mean, and when you take these toroidal compactive, so I guess like how you should think about what this compactification is doing roughly, right, is I'm giving you a bunch of cones, and these rational polyhedral cones are specifying toric varieties. And the fact that they intersect nicely and behave well with respect to the GLGZ action is going to let you glue them together in a way to form a compactification.
So you're saying that toric varieties form the boundary?
Yeah, I'm saying so that the toroidal compactive, locally, the boundary divisor is a toric, looks like a torus inside a toric variety. And the reason, the reason that's important in part is that resolving, if that's singular, a very simple way to resolve that, right, is just to take your cone and subdivide it with a barycentric subdivision until your cone is simplicial. And then then your life is, you have more toric varieties, but now all of a sudden everything is smooth.
I think one of the really significant things in your proof was the fact that your tropical compactification had a kind of homotopy invariance.
Yes.
And this was very good because then you could subdivide.
Yep, and that's exactly the important thing, right? There is certainly something subtle kind of going on here since the compactification is not smooth.
Well, if there's no other further question, I think we just thank our speaker again. Thank you very much.
Thank you so much for the opportunity to speak.
And we'll just say goodbye, I guess. Bye-bye.
Bye.
Thanks for the talk.